What's up, y'all? We are going to do what's called a logistic growth model. Um, the easiest way to think about it is it's a population model with a carrying capacity. So, with limited resources in an ecosystem that some population lives in. There's lots of other ways that we can apply it, but for now, that's what we're going to focus on. So what I would like you to do is use separation of variables to solve this equation right here. And before you go off and do that, I'm going to give you one tip. When you do your separation of variables, leave this 1/5 on the right side, on the t side. It'll make it easier for you to get to your solution. So go ahead. I want you to hit pause and find a function p of t given these initial or these conditions right here. So hit pause. Here comes your solution so you can check your work. Okay, hopefully you got p of t is 3e to the 1/5 t. I actually have a slope field over here. This green line right here is 3e to the 1/5 t. If I had different initial conditions, we could have different curves that would fit it. So all of these that I'm drawing in right here are called solution curves, right? This one would have p of 0 maybe equal to 9 because it goes through right here. And this one would have p of 0 is, a little bit less than 6, so 5.9. That would be right here. What's the general form of this thing? Well, if I were to have dp dt equals k times p, you could solve that and get p of t with p of 0 equal to p naught would be p naught e to the kt. A lot of times we call that poked. So the poked equation is just comes from some separation of variables. What I want to talk about with this thing here is that it doesn't have a carrying capacity. If I were to continue drawing, these graphs right here, they would just keep going up, right? And they would never flatten out. So they assume that there's nothing limiting the growth of these populations, which in some scenarios makes sense, but in other scenarios we can add in different parts of the model. So I'm going to give you a new equation here that has a carrying capacity. This one will be, go to green, and this is a logistic model right here. P of t equals, or sorry, not P of t, dp dt, which is the growth rate over time, is equal to 0.001 times p, open parentheses, times 500 minus p. This number could be smaller or bigger or whatever. Really, the key is that I've got the p here and the something minus p here. This part right here, notice if I get rid of this, that is this model right here, instead of a 1/5, it's got a 0.01, right? So that part of it is going to make it grow. And then this part right here actually creates the carrying capacity. So let me show you how that does that. What I'm going to do to start is build out a graph like this without all the little slope field pieces. So just a bunch of solution curves. One thing I should comment about with this one that'll help us as we're down lower is notice if the population is 0, then the growth rate is 0. How does that show up? It shows up right here. Notice all these little slope field lines are small. And then as the population gets bigger, the growth rate gets bigger. And that shows up by like, all right, I go from 0, now I have a positive slope. Now I have a positive slope that's a little bit bigger. And the further I go up on this graph, the higher the slope is, the bigger the rate of change is with respect to time. And remember, this is my time axis, and that's my p-axis. All right, so let's go down here and build that out for this equation that we have right here. All right, I am going to draw, I'm going to draw a p-axis. And then I'm going to go and draw a t-axis. And then I'm going to let each of these be 100 because this 500, I want to include it up there. So 100, 200, 3, 4. That's my 500. Make it a little bit darker so we don't miss it. 600, 700. So if I have something with a carrying capacity, then if we start less than that carrying capacity, then the population is probably going to go up to it. If we start above the carrying capacity, there's not enough space for everyone, or whatever the population is, so it's going to go down. So just like up here, if I make p equal to 0, dp dt is 0. Same thing happens here. Let's go green. dp dt evaluated at p equals 0. Well, notice that gives me a 0 here, multiplies by that, and gives me 0. So what does that mean? It means if the population starts at 0, it doesn't go anywhere. So we're just going to have a flat line there. That's actually a solution curve, just like these three here are all solution curves. So I'm going to draw a bunch of solution curves that will help us visualize what's going on here. So can you spot another value of p that will give me a rate of change equal to 0? Oh, look, 500. So dp dt evaluated at p equal to 500 is also equal to 0, because if I plug in 500 here, I get a 0. Zeros like these things, it gives me dp dt. Notice dp dt, the slope is dependent on the y-axis height. It's not dependent on the side to side. So I'm going to draw another solution. Whoops, let me switch to blue. I'm going to draw another solution curve in like this. That means that if the population starts at the carrying capacity, it doesn't leave that value, right? Maybe in reality it would like hop up and down, right? But in general, that population is going to stay at that value, right? Maybe we're talking about bacteria in a cup, and each unit of population is like 10,000, I don't know, whatever, bacteria, right? So we would stay with that 500, right? All right, so now let's look at some other dp/dt's, right? So notice I'm plugging in different values of p, and that's going to give me my slopes, right? So I want you to see that if we are here or if we are here, right? If we are very close to that 500 or very close to the 0, dp dt is approximately 0. Actually, it's just a bit bigger than 0. It is positive. Well, I'm just saying it's positive. Why is that? Well, look. Say I plug in 1. We'll come down here. We'll do it right here. dp dt evaluated at p equal to 1. All right. So look, I get 1 there. I get 500 minus 1, so that gives me 499. So if I do that, I get 0.001 times 499. Now I'm going to show you, well, you guys know how to multiply this. What I like to do is go 1, 2, 3. I move that decimal 3 times. Then I grab this decimal place and I go 1, 2, 3. So what's that give me? It gives me 0.499. So the slope when I've got a population of 1 is going to be very, very small. I would argue that we would get the same value if I evaluated this at 499. If I did p of 499, this is the same as, all right, well, dp dt evaluated at p equal 499. Why is that? Because look, if I subtract here, I get my 1, which is the same as the one that I had here, right? And then if I make p equal to 499, I'll just write it out. It's 0.001 times 499 times 1 if I plug that in. And notice it's just a flipped version of what I had on the previous one. So the slopes are actually symmetric. Say I were to look at the slope at 10, it would be the same as the slope at 490. Okay? Let's look in the middle. So let's look at dp dt evaluated, at p equal 250. But I want you to see, I get 0.001 times 250 times 50 minus 250. So that gives me 250 squared times 0.01. What is that? It's big. And what else is it? It's positive. Um, I'm going to draw a couple solution curves in that fit those ideas that I just said. One, there's symmetry in terms of the slope. The slope here is going to be the same as the slope here in terms of like the distance from this down and from this up. I get a really big slope here. It's small here. It's small here. Let me draw in a curve that fits that idea. I'm going to try at least. So those are all solution curves, just like we had solution curves up here. Notice they actually look exponential at first, but then they sort of flatten out, okay? And they hit that carrying capacity. The steepest slope is right here in that middle point. That would be the dp dt at 150. Did I give initial conditions? I did not yet. So, but say I had an initial condition of 100, right? Well, it would kind of pick up at that slope right there because I would have had a graph that would have fit it like this, right? And then it goes up and then over like that. Now let's talk about what happens above this carrying capacity line of 500. Let's plug in 100. All right, come down here. dp dt equals, or sorry, evaluated at 600 is equal to, so that's 100 above the 500, 0.001 times 600, which is going to give me 6.6, 1, 2, 3, okay, times 500 minus 600. What I want you to see is that this is negative. This piece is always going to be positive because we're always above that 500, so these numbers are always going to be positive. But then if I take 500 and subtract something that's above 500, it's going to be negative, okay? What that means is that we've got things that are going down. And again, just like if I have a value very, very close to this line, the slope's going to be 0. So the curves that I get from above this are going to come in, that's poorly done, are going to come in and flatten out like that. Say we started with a population of like 1,500, it would plummet until it got closer to the 500, and then it would slowly approach that 500. So you can see that as long as we are talking about a population that starts at a positive value, no matter what the initial starting point, whether it's 1 or whether it's 100 or 400 or 700 or 1,500 way up top, all of them are going to go to that carrying capacity of 500. I hope that that idea and this graph makes sense from this equation right here. In the next video, I'm going to show you how we start with an initial condition, and I believe we're going to start with 100, so we're going to find the equation of this curve right here. If we start with an initial condition, what is the equation? How can I use separation of variables to get the equation of P of t? Just like up here, we started with dp dt, but we eventually got poked, right? So what would the poked version be for this equation right here? And don't worry, we're not going to do it with k's and t's. We're going to do it with numbers like we did right there. So see you in the next video.